Hello everyone, welcome to Gamma Classroom. Today I'm going to introduce Ohm's Law Part 1. 1.2-1 How voltage, current, and resistance relate. This is the electrical circuit. We learned this circuit in previous videos. This is the battery, and this is the lamp. They are conductors connected to the two devices, battery and lamps. Free electrons will continually moving in this way, like this. This is the conventional rotation. This continual movement of free electrons of a circuit is called a current. We call this the current. And it is often referred to in terms of flow. This is called the flow, current flow, like this way. Just like the flow of a liquid through a hollow pipe, like this water flow will go this way. We call this flow. We call this way current flow. This way. The force motivating electrons to flow in a circuit is called voltage. Voltage is a specific measure of potential energy that is always relative between 2 points. When we speak of a certain amount of voltage being present in a circuit, we are referring to the measurement of how much potential energy exists to move electrons from one particular point in that circuit to another particular point. Without reference to two particular points, the term voltage has no meaning. We know this is the electric circuit, and this is the pump system. This is the pump. We learned this before. This is the pump is similar with the voltage. And this is the reservoir. The water in this reservoir have the potential energy because here is higher than this level. So the water will flow through the pipe, go down like this too, like this. And the voltage is exactly the same with this the potential energy. If the distance between these 2 points is higher, the potential energy is bigger. It's the same if the voltage is higher and between these 2 points the potential voltage is higher. This 2 is exactly the same. Free electrons tend to move through conductors with some degree of friction or opposition to motion. This opposition to motion is more properly called resistance. The amount of current in a circuit depends on the amount of voltage available to motivate the current, and also the amount of resistance in the circuit to oppose current flow. Just like voltage, resistance is a quantity relative between 2 points. For this reason, the quantities of voltage and resistance are often stated as being between or across 2 points in a circuit. To be able to make meaningful statements about this quantity in circuits, we need to be able to describe their quantities in the same way that we might quantify mass, temperature, value, length, or any other kind of physical quantity. For mass, we might use the units of kilogram or gram. For temperature, we might use degrees Fahrenheit or degrees of Celsius. Here are the standard units of measurement for electrical current, voltage, and resistance. The symbol given for each quantity is the standard alphabetical letter used to represent that quantity in an algebraic equation. Standardized letters like this are common in the discipline of physics and engineering and are internationally recognized. The unit abbreviation for each quantity represents the alphabetical symbol used as a shorthand notation for this particular unit of measurement. Let's take a look at this table. This is a quantity. This is a symbol. This is a unit of measurement, unit abbreviation, and example. Let's take a look at the current. We use the symbol use I because this means intensity, I. The unit of the measurement use amp or use amp. In all the electrical article or engineering drawings, we always use the amp. Amp. The unit of abbreviation is amp. But we say this is the letter A, but we never say this is A. For example, when you see the fuse is 1 amp fuse, you never say 1 A fuse. It's strange. For example, it's 50 amp fuse. The amp means it's ampere. So you go to the Home Depot to see the fuse. Everything is 1 amp or 50 amp or 20 amp fuse, not 1A fuse. Similar with the voltage. The voltage we use the E or V as a symbol. It means it's watt. The unit abbreviation is V, watt, means watt. We never pronounce it V, we pronounce watt. For example, the battery, we see the battery is 1.5 watt or 9 watt. Sometimes we see the power in our house is 120 watt, means it's watt here. Never say 120 V. And the resistance, use the simple R, means it's resistance. The unit of measurement is ohm. Ohm. And the unit use this one. This is the Greek letter. Pronounces the omega. But in the electrical article, everything, you never pronounce omega. You pronounce ohm. For example, the resistor is 10 ohm, 500 ohm. Never say 10 omega, 500 omega. That's crazy. So 10 ohm and 500 ohm means this unit. Each unit of measurement is named after a famous experimenter in electricity. The amp after the Frenchman Andrew M. Ampere. The watt after the Italian Alessandro Watt, and the ohm after the German Georgia Simon Ohm. The mathematical symbol for each quantity is meaningful as well. The R for resistance and the V for voltage are both self-explanatory, whereas I for current seems a bit weird. The I is thought to have been meant to represent intensity of current flow, and the other symbol for voltage E stands for electromotive force. The symbols E and V are interchangeable for the most part. Also, some texts reserved E to represent voltage across a source, such as a battery or generator, and V to represent voltage across everything else. All of those symbols are expressed using capital letters, except in cases where a quantity, especially voltage or current, is described in terms of a brief period of time. Call it an instantaneous value. For example, the voltage of a battery, which is stable over a long period of time, will be symbolized with the capital letter E, while the voltage peak of a lightning streak at the very instant it hits a power line would most likely be symbolized with the lowercase letter e or lowercase v to designate that value as being at a single moment in time. This same lowercase convention holds true for current as well. The lowercase letter I representing current at some instant in time. Most direct current DC measurements, however, being steep over time, will be symbolized with capital letters. One foundational unit of electrical measurement, often taught in the beginnings of electronics courses, but used infrequently afterwards, is the unit of the current, which is the measure of electric charge proportional to the number of electrons in an imbalanced state. 1 coulomb of charge is equal to 6.25 times 10 power 18 this one, electrons. The symbol for electric charge quantity is the capital letter Q, with the unit of currents abbreviated by the capital letter C. It so happens that the unit for current flow, the amp, is equal to 1 coulomb of electrons passing by a given point in a circuit in 1 second of time. That means 1 amp equal to 1 coulomb per 1 second. 1 coulomb means 6.25 times 10 power 18 electrons, and the time period is 1 second. Cast in those terms, current is the rate of electric charge motion through a conductor. As stated before, voltage is the measure of potential energy per unit charge available to motivate electrons from one point to another. Before we can precisely define what a watt is, we must understand how to measure this quantity we call potential energy. The general metrical unit for energy of any kind is the joule, equal to the amount of work performed by a force of 1 Newton exerted through a motion of 1 meter in the same direction. In British units, this is slightly less than 3/4 pound of force exerted over a distance of 1 foot. Put in common terms, it takes about 1 joule of energy to lift a 3/4 pound weight 1 foot off the ground, or to drag something a distance of 1 foot using a parallel pulling force of 3/4 pound. Defined in these scientific terms, 1 watt is equal to 1 joule of electric potential energy per or divided by 1 coulomb of charge. Thus, a 9-watt battery released 9 joules of energy for every coulomb of electrons moved through a circuit. These units and symbols for electrical quantities will become very important to know as we begin to explore the relationships between them in circuits. The first and perhaps most important relationship between current, voltage, and resistance is called Ohm's law, discovered by George Simon Ohm and published in his 1827 paper, The Algebraic Circuit Investigate Mathematically. Ohm's principal discovery was that the amount of electric current through a metal conductor in a circuit is directly proportional to the voltage impressed across it for any given temperature. Ohm expressed his discovery in the form of a simple equation describing how voltage, current, and resistance interrelate. Thus, E equal to I times R. In this algebraic expression, voltage E is equal to current multiplied by resistors. Use algebraic technicals. We can manipulate this equation into two variations, solving for I and for R respectively. If you know voltage and resistors, then you can get the I just simply E divided by R. If you know the voltage and the current, then you can get the resistance R equal voltage divided by current. Let's see how these equations may work to help us analyze simple circuits. In this circuit, there is only one source, the battery here. There is only one resistor source, it's the electric lamp. This one. This make it very easy to apply Ohm's law. We know this cycle is running like this. The battery puts the electrons free through the resistor, go back to the battery. If we know values of any two of the three quantities, is voltage, resistors, and current in this circuit, we can use Ohm's law to determine the third one. In the first example, we will calculate the amount of current I in a circuit, giving values of voltage E and resistance R. This is the circuit. We already know the battery voltage is 12 volt, and the resistance in the lamp is 3 ohm. What is the current? What is the amount of current I in this circuit? We can use this formula. I equal to E divided by R is equal 12 volt divided by 3 ohm equal to 4 amp. So the current in this circuit is 4 amp. In this second example, we will calculate the amount of resistance R in a circuit, giving value of voltage E and current I in the circuit. The battery voltage is 36 volt, and the current in this circuit is 4 amp. What is the resistor's value? What is the amount of resistance R offered by the lamp? We can use this formula. R equal to E divided by I. Since the voltage of the battery is 36 volt and the current in the circuit is 4 amp, then the resistance value equals 9 ohm. In the last example, we will calculate the amount of voltage supplied by a battery, giving values of current I and resistance R. We know in this circuit, we know the current is 2 amp and the resistance is 7 ohm. What is the battery voltage value? What is the amount of voltage provided by the battery? We can use the formula E equal to I multiplied by R. Since the current is 2 amp and the resistance is 7 ohm, we get the number is 14 watt. So the battery voltage is 14 watt. Ohm's law is a very simple and useful tool for analyze electrical circuit. It is used so often in the study of electricity and electronics that it needs to be committed to memory by the serious student. If you want to do the electrical job in the future, you must know the Ohm's law, because you will use the Ohm's law to do your job frequently, very often. A lot of things you need to do the calculation, use Ohm's law. For those who are not yet comfortable with algebra, there's a trick to remembering how to solve for any one quantity, given the other two. First, arrange the letters E, I, and R in a triangle like this: E, I, R. If you know E and I, and wish to determine R, just eliminate R from the picture and see what's left. Just take this one off. After you take this one off, you left E. This is I. E is on the top and I is on the bottom. So R is equal to E divided by I. If you know E and R and wish to determine I, just eliminate I. See what's left. After you take the I off, you left E and R. E is on the top and R is on the bottom. So I equal to E divided by R. Exactly like this, you see. Lastly, if you know I and R, and wish to determine E, just eliminate E and see what's left. You see, after take the E off, you left I and R. I and R is in the same neighbor. So E is equal to I times R. Eventually, you will have to be familiar with algebra to seriously study electricity and electronics. But this tip can make your first calculations a little easier to remember. If you are comfortable with algebra, all you need to do is commit E equal to I multiplied by R to memory and then derive the other two formula from that when you need them. Let's continue 1.2-2, an analogy for Ohm's law. Ohm's law also makes intuitive sense if you apply it to the water and pipe analogy. If we have a water pump that exerts pressure voltage to push water around a circuit current through a restriction or resistance, we can model how the three variables interrelate. If the resistance to water flow stays the same and the pump pressure increases, the flow rate must be also increase. That means pressure increase. If the resistance is the same, the flow rate will be increase. The same if the resistance is the same. When the voltage increase, then the current will be increased too. According to this formula, E equal to I times R. If R is the same and increase the current, the voltage will be increased too. If the pressure stays the same, and the resistance increase, making it more difficult for the water to flow, then the flow rate must decrease. This should be decreased. The same if the voltage is the same and increase the resistance, the current must be decreased. According to this formula, E if the same, when the resistance is increased, the current must be decreased. If the flow rate were to stay the same, will the resistance to flow decreased, the required pressure from the pump would necessarily decrease. If the flow rate keeps the same, when the resistance decreased, the pressure from the pump will decrease too. The same in the Ohm laws. So when the current keeps the same in the circuit, when the resistance decreases, the voltage will be decreased too. Let's see this formula. If the current here keeps the same, when this resistance decreases, the voltage should be the same, will be decreased. As odd as it may seem, the actual mathematical relationship between pressure, flow, and resistance is actually more complex for fluids like water than it is for electrons. The mathematics of Ohm's law is very straightforward and simple. Let's continue on 1.2-3, Power in Electric Circuits. In addition to voltage and current, there is another measure of free electron activity in a circuit: power. First, we need to understand just what power is before we analyze it in any circuits. Power is a measure of how much work can be performed in a given amount of time. Work is generally defined in terms of the lifting of a weight against the pull of gravity. The heavier the weight or the higher it is lifted, the more work has been done. Power is a measure of how rapidly a standard amount of work is done. For American automobiles, engine power is rated in a unit called horsepower, invented initially as a way for steam engine manufacturers to quantify the working ability of their machines in terms of the most common power source of their day, horses. 1 horsepower is defined in British units as 550 feet-pounds of work per second of time. The power of a car's engine would indicate how tall of a hill it can climb or how much weight it can tow. But it will indicate how fast it can climb a specific hill or tow a specific weight. The power of a mechanical engine is a function of both the engine's speed and its torque, provided at the output shaft. Speed of engine's output shaft is measured in revolutions per unit, or RPM. Torque is the amount of twisting force produced by the engine, and it is usually measured in pound-feet or pound-lb-feet, not to be confused with foot-pounds or foot-pounds, which is the unit for work. Either speed nor torque alone is a measure of an engine's power. A 100 horsepower diesel tractor engine will turn relatively slowly but provide great amounts of torque. A 100 horsepower motorcycle engine will turn very fast but provide relatively little torque. Both will produce 100 horsepower, but at different speeds and different torque. The equation for shaft horsepower is simple. Horsepower equal to 2 pi st divided by 33,000, where S is shaft speed in RPM, means revolution per minute, and T is shaft torque in pound-foot. Notice how there are only two variable terms on the right-hand side of the equation, S and T. All the other terms on that side are constant. 2 pi and 33,000 are all constants. They do not change in value. The horsepower varies only with changes in speed and torque. Nothing else. We can rewrite the equation to show this relationship. Horsepower is proportional to S and T. This symbol means proportional to, means horsepower proportional to S, the speed, T is the torque. Because the unit of the horsepower doesn't coincide exactly with speed in revolutions per minute multiplied by torque in pound-feet, we cannot say that horsepower equals S times T. However, they are proportional to one another. As the mathematical product of ST changes, the value for horsepower will change by the same proportion. In electrical circuits, power is a function of both voltage and current. Not surprisingly, this relationship bears striking resemblance to the proportional horsepower formula above. It means power equal to I multiplied by E. In this case, however, power P is exactly equal to current I multiplied by voltage E, rather than merely being proportional to IE. When use this formula, the unit of measurement for power is the watt, abbreviated with the letter W, but we never pronounce W, we call watt. It must be understood that neither voltage nor current by themselves constitute power. Rather, power is the combination of both voltage and current in a circuit. Remember that voltage is the specific work or potential energy per unit charge, where current is the rate at which electrical charges move through a conductor. Voltage specific work is analogous to the work done in lifting a weight against the pull of gravity. Current rate is analogous to the speed at which what weight is lifted. Together as a product multiplication, voltage, work, and current rate constitute power. Just as in the case of the diesel tractor engine and the motorcycle engine, a circuit with high voltage and low current may be dissipating the same amount of power as a circuit with low voltage and high current. This the amount of voltage alone, though the amount of current alone indicates the amount of power in an electrical circuit. In an open circuit, where voltage is present between the terminals of the source, and there is zero current, there is zero power dissipated no matter how great that voltage may be. Since P equal to I multiplied by E, and when I equal to 0, we know anything multiplied by 0 is 0. The power dissipated in any open circuit must be 0. Likewise, if we were to have a short circuit constructed of a loop of superconducting wire, absolutely zero resistance, we could have a condition of current in the loop with 0 voltage, and likewise no power would be dissipated, since P equal to I multiplied by E, and E equals 0, and anything multiplied by 0 is 0. The power dissipated in a superconducting loop must be 0. Whether we measure power in the unit of horsepower or the unit of watt, we are still talking about the same thing. How much work can be done in a given amount of time? The two units are not numerically equal, but they express the same kind of thing. In fact, European automobile manufacturers typically advertise their engine power in terms of kilowatt or thousands of watt instead of horsepower. These two units of power are related to each other by a simple conversion formula. Means 1 horsepower equal to 745.7 watt. So our 100 horsepower diesel and motorcycle engines could also be rated as 74,570 watt engines, or more properly as 74.57 kilowatt engines. In European engineering specifications, this rating would be the norm rather than the exception. This is all that we should learn today. Let's review the main points that we already learned in this video. Number 1, voltage measured in watts, symbolized by the letters E or V. Number 2, current measured in amperes, symbolized by the letter I. Number 3, resistance measured in ohms, symbolized by the letter R. Number 4, Ohm's law is E equal to I multiplied by R, or I equal to E divided by R, or R equal to E divided by I. Number 5, with resistance steady, current flows voltage. An increase in voltage means an increase in current, and vice versa. Number 6, with voltage steady, changes in current and resistance are opposite. An increase in current means a decrease in resistance, and vice versa. Number 7. With current steady, voltage flows resistance. An increase in resistance means an increase in voltage. Number 8. With current steady, voltage flows resistance. An increase in resistance means an increase in voltage. Number 9. Power is the measure of how much work can be done in a given amount of time. Number 10. Mechanical power is commonly measured in American in horsepower. Number 11. Electrical power is almost always measured in watts, and it can be calculated by the formula P equal to I multiplied by E. Number 12. Horsepower and watts are merely two different units for describing the same kind of physical measurement, with 1 horsepower equaling 745.7 watts. Thank you for watching. See you next time.